Teacher, teacher.
All right. So we're getting ready to start the downhill slide on the midterm because today is the tipping point where we're sliding down to get the rest of the chapter 10. End of the month, we will test on chapter 10. And anybody got any questions? All right. So today we're just going to have a little preview of what's to come in the main lesson. And what I'm going to do, I'm going to look at a little bit in the actual textbook that comes with this, and then also in the Alex, there's a few nice questions in there. I'm just going to try to take it very slow on far as looking at this stuff, because in the 7 o'clock hour, I'll go over officially the 10.4 section, but this time we're just going to get a preview of it. And so really what we're doing here is we're conducting probability by using the sample space. All right. And we can't always look at the sample space because if the sample space is very large, it doesn't do us very much good. The sample space is just for visually being able to look and determine how much is in the sample space and then how much is in any particular event. We'll look next time on Thursday about how we handle it if we don't have a sample space, because usually that's the case. We don't really have the sample space. We just need to know how many. Uh, All right, so a tree diagram is just a way to visually determine the number of outcomes that you have for particular experiments. Okay, and it's like when we combine into experiments, like when we use the multiplication rule. All right, Monet, that's all right. Just come back in if you can. All right, so this is an example on the screen there of a tree diagram, and I'll just kind of break it down what you got. All right, this is for a family that's that has or will have 3 children. So what we're going to have is all the possible outcomes that could happen with this. So if you look here on the first child, well, for the first child, you have a choice of boy and girl. Now, you don't necessarily get to make that choice. I know that maybe there's ways to kind of increase your probability, but whether those works, which is a question. So, boy, girl. Then on the second child, if the first one was a boy, we still have the boy girl choice for the second child. Same thing. If the first child was a girl, then you're going to still have that same choice, boy or girl. And then for the third child, each one of those 4 has the choice of boy, girl, boy, girl, boy, girl. All right. And you can kind of see here how this works. So you got 2 choices. You got 2 choices. And then you got 2 choices. So multiplying them all together with that multiplication property or the counting principle, we have 8. 2 times 2 is 4. 2 times 4 is 8. And you can see those 8 choices right here. You can see boy, 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 girl, boy, girl, boy, boy, girl, girl. And then on the second, where we start with the girl as the first child, girl, boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. So those are the 8 possible outcomes if you got 3 children. All right. Now, this same kind of tree, it doesn't matter, as we'll see, what the choices are, whether it's boy or girl, head or tail. We're going to find out too. There's another one with like a game of pool. Um, one or the other person is going to win the game of pool. There's only 2 choices. So that's why this right here, this multiplication property works, because each time we've got 2 choices, 3 times, or 2 to the 3rd power, gives us 8. All right, so that's the sample space for the 3 children, and it's very similar to some other ones, as we'll see. Let's go on down here. This is another 2 experiments. It's flipping a coin and then rolling the 6-sided die. So now, when we roll, when we flip that coin, we've got 2 choices. We've got head and tail. If we flip a head and then we roll our coin, our die, we've got 1, 2, 3, 4, 5, 6 choices. Same thing. If we flip the tail on the coin, we've still got 6 sides on the die possible. All right, so that gives us 2 times 6 gives us 12
another potentially devastating hurricane
outcomes.
And senior national correspondent Peter Zampa joined us live from New
And
York.
hopefully you can see.
Peter, thank you for joining us. So, what's the federal response as Hurricane Milton moves closer to landfall? Yeah, Megan Lee, well, if it's any indication how short this storm might be, the president today confirming he is postponing.
And here are the 12 choices. You got head 1, head 2, head 3, head 4, head 5, head 6, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. That's the 12 outcomes. So let's see if we can answer a couple of questions. I thought there was a couple in here. Well, we'll just go. I'm just going to go through these and then I'll go over to the Alex and look at a few things. And sometimes you can just look at a table and see everything. Okay. This is a table of a deck of cards. The deck of cards has 3 suits of 13, 13 hearts, 13 aces, 13 spades, 13 clubs, and so 4 times 13 is 56. So this is a deck of 52 cards. All right. So let's look at a couple of these and just get our feet wet with a little bit of probability here. All right. So let's see if we can handle this. So these over here, ace is like the first one, and then all the other ones are numbered up to 10, and then jack is 11, queen is 12, and the king is the 13th card, 4 times. So let's see if we can find out some of these things. A card is drawn from an ordinary deck. Use the sample space up here to find the probability of getting a jack. Well, we need to figure out how many jacks there are. All right, there's 4 jacks. So then the probability of a jack we got 4 of them over a total of 52. And so this simplifies because 4 goes into 52 13 times, and then 4 goes into itself 1 time. Now keep in mind that in 10.1, there was you didn't have to simplify the fractions. In other words, they would have accepted 4 over 52. But we are going to, from here on out, you're simplifying them down as far as you can. So when it says exact and simplify, then we can no longer have a common factor between numerator and denominator. 4 goes into 52 13 times, 4 goes into itself once. So therefore, this is our probability. And you can also see it proportionally, because if you look at any one of these 4 suits, there's exactly 1 jack out of the 13 cards. All right, so let's see. The next one is a 6 of clubs. All right, this time there's only 1 6 of clubs. So that's going to be so there's only one of those out of the 52. All right, and then the other one is a 3 or a diamond. Now we got to watch out because we're using essentially our or our union here. So a 3 would be these right here. It doesn't say specific what 3. It just says a 3 or a diamond. All right, so we're going to count those, of course, by what we learned back in chapter 2 when we put to find the number of elements in the union. You don't count things twice, which is why you subtract anything that's in the intersection. So we've got 13 here, 14, we already counted that one. So 15, 16. Three or diamond. All right. So as I said, there's 16 of those because we got 13 diamonds. We got the 3 of hearts, so that's 14. We got the 3 of spades, which is 15, and the 3 of clubs gives us 16. So 16 over 52. And again, we're always going to simplify these now. So 4 goes into 16 4 times. And into 52 13 times. And there we go. No longer possible to take out any common factors. All right, does those make sense? Anybody got any questions about that? How I'm getting those numbers? All right. And then the last thing I'll mention is this 2 dice. We've looked at things before where you had 1 die with just 6 sides. But now if we've got 6 die, 2 die with each 6 sides, then we've got 6 times 6 is equal to 36. And they tell you down here about there's a different experiment they want you to try, but you're using the fundamental counting principle to tell you how many total there are. So see, you got 1, 2, 3, 4, 5, 6, 6, 12, 18, 24, 30, 36 choices. Up here, these are the ones that have one, it's just label one is red and one is blue, just so you can distinguish. But this one is where the red is always the one. You do have the one where we got the red, blue, so that's 1, 1. But everything else on the blue is the 2, 3, 4, 5, and 6. Each row represents a number on the die. All the 3s, all the 4s, all the 5s, all the 6s. All right. So let's use this and see if we can answer a couple of questions. All right, here we go. So this right here is talking about the 2 dice up there. I'll bring it back up as we hit it. When 2 dice are rolled, find the probability of getting a sum of 8. Well, let's bring this up. Now, the sums are like this. 1 plus 1 is 2. I'll tell you what, let me use a different color. So 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. 1 plus 6 is 7. So you notice that the least one, the 1, 1, snake eyes, has a sum of 2. All the way out to 1 and 6 has a sum of 7. Same thing's going to happen on each one of these. So this is 3, 4, 5, 6, and 7. Same thing's going to happen here, except it's going to start at 3 rather than 2. So 3, 4, 5, 6, 7, and 8. And see, the same thing's going to happen here, except it's starting at 1 less. There's a pattern to it. 6, 7, 8, 9. Down here we got 5, so it's going to start at 6, 7, 8, 9, and 10. 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11, and finally 12. And the lowest sum is 2, the highest sum is 12. All right. So let's see if we can answer a couple of those questions. All right. So the question we want to find here is a sum of 8. We want to find the probability of a sum of 8. All right. So let's see if we can find the ones that have a sum of 8. Well, this one has a sum of 8 right here, 6 plus 2. 5 plus 3 is 8. 4 plus 4 is 8. The reverse, 3, 5 is also 8. And then 2, 6 is 8. So we have 1, 2, 3, 4, 5 values on the 2 cubes that add up to 8. So 5, and the total is 36. So there's 5 total And then there's a total of 36. All right. Nothing to simplify because there's no common factor between 5 and 36. All right. So the next one is doubles. So I'm going to find the ones that are doubles. Let me bring it back up here. The ones that are doubles. There's a double. The snake eyes, we got double 2. We got double 3. We got double 4. We got double 5 and double 6. And how many is that? 1, 2, 3, 4, 5, 6. So there's 6 of those. So there's 6 over a total of 36. And 6 goes into 36 6 times and into itself once. Okay. So 1/6 to roll doubles. Let's see, a sum less than 5. So let's bring that board back up. And we need less than 5. Now, what I'm going to do here, I'm trying to find a good way to. It was okay, less than 5. Okay. So this line right here is the 5 line. See that? Not exactly neat, but see if I can do a little bit better with a different color. So right here, I'm going to just put a straight line. So there, a line is through the ones that are a sum of 5. Now, we don't want all of those. We want the ones that are what? Let's go back to that. A sum less than 5. Okay, so let's go back over here. So all of these over here, these are the 5. This is the divide line between 5 and not 5. So over here, these are all the 6s. We got the 7s in a row, 8s and 9s. The higher ones over here, it said less than 5. So we're talking about this one. This one, this one, this one, this one, and this one. So we got these 3, 2, 5, and 1 is 6. So again, we've got 6 of them that sum to less than 5. So let's go down here and do that. And it's going to be a very similar probability. So less than 5, not an equal to. So there were 6 of those over 36, which again is 1/6. So that's how probability works. And especially since we've got the sample space here, we can go and look and see. All right. So, so that's pretty much it. Let's go over now to the Alex and let's work on a few problems. So on Thursday, I'm going to give you an assignment this time, and it's going to be this one. So be at the first part of class. So just remember this to make it go a lot smoother for you. All right. So 3 computers are chosen at random from an inventory of Dell and Acer computers for a bookstore display. Assume the same number each brand of computers is in stock. In other words, the probability is the same. It's going to be you're going in there and it's going to be half Dell and half Acer. All right. So what I'm going to do is I'm going to go ahead and try to draw out this little thing. So they can get cramped really quick. So this is why it's not really feasible to do this for um, every kind of problem. That's why we just go to those counting methods to do it. All right. So I'm going to put on here. I'm going to put D and A. So this would be the Dell and Acer. So this is the computer 1. So Dell, Acer. Computer 2 is going to do the same thing. So Dell and Acer. Dell and Acer. And then we're going to do the same thing for computer 3. Dell and Acer. Dell, Acer. Dell, Acer. Dell and Acer. All right. So then what I got here, I'm going to have the sample space. The first one would be Dell, 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 just like when we did that with the boy and girl, 3 boys. So Dell, Dell, Acer. All right. So now we got this first one and then this little piece. So now we're going D, A, D. And then we got D, A, A. And then that's 4 for the first one being Dell. So now we're going to start ones with Acer. So A, D, D. And then A, D, A. A, A, D. And then last one is AAA. And again, you got 2 times 2 times 2 is equal to 8 outcomes. And here they are: 1, 2, 3, 4, 5, 6, 7, and 8. All right, so now let's answer these questions. All right, so the probability that all 3 will be dells, well, how many are all 3 dells? Well, the D is del, and there's only one of those, D, 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 out of the 8. So 1 over 8. Only one with all 3 dells. All the other ones have an acer in it somewhere. The probability that exactly 2 will be acers. 2 be acers. Well, let's find those. So that means we've got to have 2 A's. That's 3 D's. This is 1A. This is 1A. Here's one with 2 A's. This has got 2 D's, so not that one. But here's another one with 2 A's. Here's another one with 2 A's. How many is that? Why don't we include that last one? Why not that one?
Because it's 3 instead of 2.
Because that one's got 3. Okay. So that's not exactly 2. It said exactly 2. The probability that at most 1 will be an acer. Now, here's what you got to think. At most 1. In other words, we don't want any more than 1 acer. We can have 0 acers, but the most acers we're going to have is 1. So this is at most 1. That's 0 acers. Here's another one. Here's another one. That's got 2, so we can't use that one. That's got 1 acer. All the rest have 2, 2, and 3. So then there's going to be 4 out of 8. And here's what I said is we've got to simplify these now. So 4/8 is 1/2. Simplified version. Oh, there was just 3 parts on that. I thought there was a third one, a fourth one. Okay. So any questions about that one? All right, so let's try another one here. All right, now I'm going to leave this on here because I'm going to use it again in a bit, so I don't have to draw again, or at least I'm not going to draw the whole thing. I'm going to keep the little tree part. I'm going to change the lettering. But for this one, they give us a sample space here. All right. Construct the sample space for a probability experiment where a coin is flipped, in other words, heads or tails, and then a 10-sided die is rolled. Well, they're giving it to us here. Coin is flipped, so that's head, and then the 10 numbers there represent the 10 sides of the coin. Over here is the tail side, and then we're also matched with the 10 sides of the die. So this setup was used for a carnival game, and different amounts paid out depending on certain outcomes. We don't need to know about that yet. All right, so we're going to try to find these probabilities. Find the probability that there was a tail on the coin and an odd number on the die. All right, so it says tail. So we're not looking at that side. That's all heads over there. Each one of those 10 has an H in front of it for the heads. Here's the one that we want to look at, this side, this 10, because we need a tail on the coin and then an odd number on the die. So odd number, odd number, odd number, odd number, odd number. So that's 1, 2, 3, 4, 5. Now, how many total do we have? You see that 10 up there, but remember, it's double because of the 2 times the 10 gives us 20 outcomes. And that's what we had here. We had 10 with the head and 10 with the tail. So what we're going to have here, oh, I'm going to do it down here. Got more room. That there was a tail on the coin. Probability of tail and odd. So now there are 1, 2, 3, 4, 5 of those out of a total of 20. And then this simplifies down to 1/4, 1/4. Okay. Questions?
No.
All right. The probability that there was a head on the coin and the prime number on the die. What exactly is a prime number? Does anybody remember that? I'm going to put 11 for right now. We don't need 11 here because there's no 11. But those are the first 5 prime numbers. It just keeps going on and on, incidentally. It doesn't stop because it's an infinite set. But we only need to have these. So now the probability head and prime. Well, let's see. How many prime numbers were there? Okay, first of all, it was head. So we're only looking at these. So there's the 2, the 3, the 5, and the 7. See, 1 only has itself. 4 divisible by 2, so you can't do that. So this is divisible by 2 and 3. 2, 8, and 4, 3 and 3, 2 and 5. So these are the only ones that we have underlined. So that's 4 over 20, which is 1/5. Okay, so let's put that in there. And then we got a last one. All right, I don't have to erase this to fit that in. So the probability that there was a tail on the coin, so it's going to be on this side. And the number, well, let's just use this one. Tail on the coin, so it's over here. And the number less than 9. So that would be this one, 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 and this one. Less than 9, not including 9. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have 8 was 8, and it's over 20. So let's see, that's going to be 4/10 or 2/5. And then one more. Oh, okay, that was it then. I thought there was one more. Yeah, just A, B, and C. All right. Now, I'm going to use this again, as I said, is this one would have worked fine with the 3 children. It'll also work for this one. I'll explain it in a second. Let me erase. All right. So on this one, we got a different scenario. But again, there's only 2 outcomes for each one of these. It says Mark and Raul play 3 games of pool, like the 3 kids, or pick the 3 computers. They're equal in ability, so we don't have to worry about probability. It's just going to be one or the other. Draw a tree diagram to represent the sample space and find the probabilities. Let M represent the event that Mark wins a game, and R represent the event that Raul wins a game. So what I'm going to do is I'm just going to put M, R, M, R, M, and R. Same thing here, all the way down. M, R, M, and R. M, R, M, R. All right. So what these are going to be are, I'm going to just type them over here. So the first one's going to be MMM, and then it's going to be MMR, and then MRM, and then MRR. So we got the first 4, which are all the ones where Mark wins the first game. So all the second half are going to start with R. So R, M, M, R, M, R, 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 M, and R, R, R. 1, 2, 3, 4, 5, 6, 7, 8, as we should have when we've got 3 separate games. And each time there is 1 or 2 people going to win the game. Mark a roll. All right. You can also put it in caps. It'll take either one. All right. So find the probability that either Mark or Raul wins all 3 games. So we got to have a run of MMM or RRR. All of these other ones in between, that's a mixture where 2 win one wins the other. I'm sorry, 1 wins 2, the other one wins the last one. In that case, you see, you always got 2 winners and 1 loser. So this right here is going to be 2 over 8, and then that simplifies to 1/4. Find the probability that either Mark or Raul win 1 out of the 3 games. All right. So I'm going to start with Mark, and I'm going to find the ones where Mark wins 1 out of 3. So here, Mark wins all 3. Here Mark wins 2. Here's it wins 2. So here's one where Mark wins 1 out of 3 games. Here's another one where Mark wins 1 out of 3 games. 1M. Here's another one where Mark wins 1 out of 3 games. All right, let's look at the other guy. Let's look at Raul. We want ones now where Raul has 1 game win. Well, there we got that one. Here's another one with just 1 R in it. Here's another one with 1 R in it. These don't have any R's. These don't have any M's. So we got 1, 2, 3, 4, 5, 6. So 6 over 8.
Wow.
So that simplifies because both of them are divisible by 2. 6 divisible by 2 3 times. 8 divisible by 2 4 times. Okay. All right. So find the probability that Mark loses only 2 games in a row. Only 2 games in a row. All right. So let's go up here. Only 2 games in a row. Loses 2 games in a row. And it's Mark. So here he wins 2 games in a row. That's not what we need. Here, however, is where Mark loses 2 games in a row because he wins the first one and then he loses the second one and he loses the third one. So on this one, Mark only loses 1 Here he loses 2, but they're not in a row. That's what it said, right? Yeah, 2 games in a row. And there's the other one. That's the only 2 where he wins. Oh, I'm sorry, he loses 2 in a row. Because when Raul wins, Mark loses. So Mark loses, Mark loses. Mark loses, Mark loses. So that's going to be 2 over 8, which is 1/4. And then the last one, find the probability that Raul wins the first game. So Raul wins the first game, loses the second game, and wins the third game. So we're looking specifically for that pattern where Raul wins first game, loses the second game, he drops it to Mark, and then the last one, he wins. So there's only one of those. You can kind of go up here and see RMR. There's only one of those. All the other ones are different. So this is all right. I'm going to go ahead and erase this part so we're not going to need it again. So this is 1 over 8. All right. Any questions about those? We're going to do one more little one. All right. So now we're going back to the dice one. I'm going to leave these up here because I think that's what happened with this? How come it's not marked as? Oh, because I didn't check the last part. All right. All right. So this is the same 36 outcomes that we have for rolling 2 die. And so we're going to handle these a bit at a time. So we want to find the probability. This is Rosie, and they're having a Las Vegas night, and craps is one of the games. So here's all the possible outcomes with craps because it's 2 dice. So we want to find the probability that Rosie gets a sum of 5. So let's see if we can find those sum of 5s again. Sum of 5. So there's a sum of 5. 1 plus 4 is 5. 2 plus 3 is 5. 3 plus 2 is 5. And 4 plus 1 are 5. So those are the only 4 that have a sum of 5. So 4 over 36 1/9. 1, 2, 3, 4. 6 times 6, 36 total. And then both are divisible by 4. 4 goes into 36 9 times, and into itself once. All right, the sum is odd. All right. Now before, I'm just going to kind of go back up here and rewrite. We had 2, 3, 4, 5, 6, and 7. Now, out of that first one, how many are odd? Well, it does say odd, right? Yeah. So this one, and this one. Well, what happens down here, it's going to be the same amount. There's 3 out of 6 because maybe you never noticed it or not, but numbers are either odd or even. There's no two choices about it. They're odd or even. So half of numbers fall into one category, half fall the other. So this is another odd one, odd one, odd one. So that's 3, 6, 9, 12, 15, 18. 18 are odd and 18 are even. All right. So then this is going to be, let me write it out. So it's going to be 18 over 36. And that's 1/2 in disguise because 18 goes into 36 twice and into itself once. Two on one or both dice. 2 on one or both dice. That's not a sum, so we don't need to. We just need to go up and find dice with 2 on them. Well, look at here. These got 2 on them. All of those have a 2 in the second or in the blue die. These right here all have a 2 on the first or the red die. This one is the both. That's your intersection right there. So what we have is we have 1, 2, 3, 4, 5, 6, 7. We're not counting that one again. 8, 9, 10, 11. So this is going to be, and we don't have to worry about simplifying this one because 11 and 36 don't have a common factor. The probability that Rosie rolled a sum greater than 12. All right, let's go back over here. Let me put some more of these back on here. So this is 2, 3, 4, 5, and then it goes all the way up to 7. These right here, this is going to be 8, 9, 10, 11, and 12. So this right here would be 10. And then I'm not going to do all of them just because I want you to see. All right. So notice what ends up happening is you have these diagonal rows of one single number. We saw that with the 5s. The same thing happens with the 9s. There's the 9s. But the question asks something that's really not possible because it says the sum that Rosie rolled is greater than 12. Well, the highest one is 12. 6 plus 6 is 12. So then this right here is good old fat 0. It's 0 over 12. I'm sorry, 0 over 36 or 0. And then lastly, the probability that Rosie rolled a 5 on one die and 1 on the other. 5 and 1. So again, this one's not sum. So she said 1 and 5, I believe. All right. So 5 on one and 1 on the other. Well, there's not too many of those, are there? There's 5 on one and 1 on the other. And here's 1 on one and 5 on the other. And that's the only two like that. So this last one is 2 over 36, which is 1/18. So there we go. So I wanted to go through these like Alex type problems that you'll be having. And on Thursday, I'm going to give you a little evaluation like this. So be prepared for that, for the first half hour of class. Anybody got any questions? That's all we're going to look at for the first hour. And at 7, I'm going to hit the formal lecture of this. So, all right. If you got any questions, stick around. Otherwise, I'll see you in a few. All right.
Mr. Michael,
Mm-hmm.
I had came in class today, so I had missed this evaluation thing, but you said towards the end of the semester they go open back up, right?
What's that?
I had missed the class, the in-class assignment because I came in late.
There was no in-class assignment today. There'll
Oh,
be one Thursday. I only give like one a week.
but
Remember,
I
you
did.
got to be here for that. All right.
I know. I gotta be there exactly at 5:30
But
because
it's not
it's open.
today. It'll be Thursday.
Okay, great.
First
Well,
half hour.
I'm gonna be here on time normally.
All right.
Thank you. See you later. In a minute.
Mm-hmm. Yeah. A few minutes.
Mr. Michael, I'm still in like almost at the end of 10.3. When I finish 10.3, that'll bring me to 10.4.
It should. They may stick some other stuff in there that you didn't master yet, but
I
yeah,
think
you'll
that's what
eventually get to
keep like
10.4.
I think that's what keep putting me behind where I am.
Yeah, I mean, with
Get
those
ready.
things, it's one of the things I tried to suggest here is try to attempt at least within 2 days of coverage in class and try to finish within 4 days. If you follow that, then you're not going to have all so much stuff in your path that's undone. But just keep working
Okay.
because it'll put you on there. All right. Well, I'll see you in a bit. Anybody else got anything? I gotta